Hi all, welcome back. In this video we are talking about Hadoop and its component. In this video we'll understand what Hadoop is, why it was created, and how its core component work together to handle big data. If you are new to big data, don't worry. I'll explain everything step by step in a simple way. So let's start. We'll start by understanding big data and the challenges with traditional systems. Then we'll briefly discuss the Hadoop ecosystem and summarize everything. Finally, we'll look at Hadoop, its architecture, and its three main components, that is HDFS, YARN, and MapReduce. So let's see what is big data. Big data refers to extremely large amount of data generated every day. This data comes from sources like social media, websites, mobile apps, sensors, and transactions. Because of its size, speed, and different format, this data is difficult to store and process using traditional systems. There are 5 V's which are used to describe why data today is considered big and why it's challenging to handle it. The first V is volume. Volume simply means the amount of data. Today, data is being generated in massive quantities, from social media posts and videos to transaction records and sensor data. We are no longer talking about megabytes or gigabytes, we are talking about terabytes and petabytes of data. Handling this much data using traditional system is extremely difficult. Let's move to the second V, that is velocity. Velocity refers to the speed at which data is generated and processed. Data is coming in very fast way, sometimes in real time. For example, think about live stock market updates or data coming from IoT devices. The challenge here is not just storing the data, but processing it quickly enough to make timely decisions. The third V is variety. Variety means the different type of data we deal with. Earlier, most data was structured and stored in tables. But today, data can be text, images, videos, audio, JSON files, logs, and much more. Managing all these different formats together is another big challenge. The fourth V is veracity. Veracity is about the quality and accuracy of data. Not all data is clean or reliable. Some data might be incomplete, duplicated, or even incorrect. So before using data for analysis, we need to clean and validate it. And the final V is value. Value is the most important V. Data itself is not useful unless we can extract meaningful insights from it. The goal of big data is to turn raw data into value like better decision, prediction, or business improvements. Now let's see the problems with the traditional systems. Traditional systems were designed to handle structured data stored in tables. As data started growing rapidly, these systems faced problems like limited scalability, high cost, and poor fault tolerance. Handling failures and processing large datasets become very difficult. To solve these problems, Hadoop was created. The idea was simple: store data across multiple machines and process it in parallel. This made it possible to handle very large dataset efficiently using low-cost hardware. So let's understand what is Hadoop. Hadoop is an open source framework developed by Apache. It is used for storing and processing large amount of data in a distributed environment. Hadoop is scalable, fault-tolerant, and cost-effective, which make it ideal for big data applications. Let's understand the architecture of Hadoop. Hadoop follows a master-slave architecture. The master node manages the system, while slave node store and process data. The core components of Hadoop are MapReduce, HDFS, YARN, and Hadoop Common. MapReduce is a framework that helps programs do the parallel computation on data. HDFS is a distributed file system that runs on a standard or low-end hardware. YARN stands for Yet Another Resource Negotiator. It manages and monitors cluster node and resources. And the last is Hadoop Common. It provides common Java libraries and script that is required by Hadoop components. Firstly, let's see in detail what is HDFS. The Hadoop Distributed File System, commonly known as HDFS, is a scalable, fault-tolerant storage system designed to handle very large datasets across multiple machines. HDFS follows a master-slave architecture and consists of three main components: the name node, the data node, and the client. At the center of HDFS is the name node. The name node acts as the master and is responsible for managing the file system's metadata. This includes information such as file names, directory, structure, block locations, and access permissions. It does not store the actual data, but it knows where every piece of data is located. The actual data is stored on data node. Data node are worker nodes that store data in the form of blocks. Each file in HDFS is divided into fixed size blocks, typically 128 megabytes, and these blocks are distributed across multiple data nodes. To ensure fault tolerance, HDFS replicate each data block across multiple data nodes. By default, each block is stored in 3 different nodes. This means that even if a node fails, the data remains available. The client is the interface through which users interact with HDFS. When a client wants to read or write a file, it first communicates with the name node to obtain metadata. Once the block locations are known, the client directly interacts with the data node to transfer the data. HDFS is designed for high throughput rather than low latency. It is optimized for large sequential reads and write, making it ideal for big data analytics and batch processing. Let's understand a scenario of HDFS. Assume we have a file of 300 MB. Then the file will be divided into 3 blocks and stored in HDFS. The first block will be of 128 MB, the second block will be of 128 MB, and the final block will be of 44 MB. Now see what is YARN. YARN manages cluster resources and job scheduling. It allows multiple processing frameworks to run on Hadoop, not just MapReduce. YARN, which stands for Yet Another Resource Negotiator, is the resource management layer of the Hadoop ecosystem. While HDFS handles data storage, YARN is responsible for managing and allocating cluster resources and scheduling jobs. YARN follows a master-slave architecture and is designed to support multiple data processing frameworks such as MapReduce, Spark, and Hive, all running on the same Hadoop cluster. The main component of YARN is the resource manager. The resource manager acts as the master and is responsible for managing the cluster resources such as CPU and memory and scheduling applications across the cluster. Each worker node in the cluster runs a node manager. The node manager is responsible for managing resources on its individual node and monitoring the containers running on that node. So when a client submits an application to the YARN, the resource manager launches an application master specifically for that application. Each application has its own application master. The application master is responsible for managing the entire execution of the application. It negotiates resources with the resource manager, decides how many tasks are needed, and coordinate where and how those tasks should run. Once resources are allocated, the application master works with Node Manager to launch tasks inside containers. It continuously monitors the progress of the task and handles failure if any occur. On the other hand, the Node Manager runs on every worker node in the cluster. The Node Manager is responsible for managing node-level resources such as CPU and memory. It launches and monitors containers, enforces resource limits, and reports the health and resources usage of the node back to the resource manager. Now let's understand MapReduce in detail. MapReduce is a processing model used in Hadoop for processing large volumes of data in a distributed manner across a cluster. It works by dividing the input data into smaller chunks and processing them in parallel across multiple nodes. This parallel processing enables Hadoop to handle very large datasets efficiently. The MapReduce process consists of two main phases: the map phase and the reduce phase. In the map phase, input data is processed and transformed into immediate key value pairs. Each mapper works independently on a portion of data. These intermediate outputs are then shuffled and sorted, grouping all values associated with the same key together. In the reduce phase, the reducer processes these grouped key value pairs to produce the final output. MapReduce runs on top of YARN, while YARN handles resource management and scheduling. MapReduce's focus purely on data processing logic. This separation allows Hadoop to run multiple processing frameworks, not just MapReduce, on the same cluster. Now let's understand MapReduce with a simple example of word count. Assume we have an input text document that contains a sentence such as Hadoop process big data and big data needs Hadoop. First, the input is split into separate lines. And then in the map phase, the input text is split into smaller chunks and each mapper processes its portion of the data. The mapper reads each word and converts it into a key value pair, where the word is the key and the value is 1. For example, the mapper produces pairs like the Hadoop 1, process 1, big 1, data 1, and so on. Next comes the shuffle and sort phase. In this phase, all intermediate key value pairs are grouped together based on their keys. This means all occurrence of the same word such as Hadoop and big are collected and sent to the same reducer. Finally, in the reduce phase, the reducer aggregates the value for each key. It sums up the count to calculate the total number of occurrence of each word. The final output is a list of words along with their total count, such as the Hadoop 2, big 2, data 2, and 1, process 1, needs 1. This example shows how MapReduce processes large datasets efficiently by breaking the work into parallel map and reduce tasks across the cluster. Now let's look at some important supporting components of the Hadoop ecosystem. First, we will talk about Apache Scoop. It is used for data transfer between Hadoop and relational database. It allows large volume of structured data to be efficiently imported into HDFS and exported back to database. Next is Apache Flume. It is designed for ingesting streaming data. It is commonly used to collect and move log data or event data from multiple sources into Hadoop in a reliable and scalable way. It is normally used for unstructured data like JSON, XML, flat file. It does not analyze the data, it just takes it from source to HDFS. It does not store the data anywhere as well. Next is Apache Hive. It provides a SQL-like query language called HiveQL, which allows users to query and analyze data stored in Hadoop without writing complex MapReduce code. Hive is widely used for data warehousing and analytical queries. Next is Apache Pig. It is a high-level data flow platform used for processing large datasets. It uses a scripting language called Pig Latin, which simplifies complex data transformations compared to writing raw MapReduce programs. Next is Apache HBase. It is a distributed NoSQL database built on top of HDFS. It is designed for real-time read and write access to large datasets and is commonly used when low latency data access is required. Next is Apache Uzi. It is a workflow scheduling system for Hadoop. It is used to define, manage, and monitor workflow that consist of multiple Hadoop jobs such as MapReduce, Hive, and Spark jobs. Lastly, we will talk about Apache Zookeeper. It is a coordination service used to manage configuration, synchronization, and leader election in distributed system. Many Hadoop components rely on Zookeeper to maintain consistency and reliability across the cluster. Together, these components extend Hadoop capabilities, enabling data ingestion, querying, coordination, and workflow management at a scale. There is a feature in Hadoop known as high availability, which was introduced in later versions of Hadoop 2.0. Let's see in detail what it is and why it is required. Before high availability existed, the Hadoop cluster had only one name node. This means that if the name node failed due to hardware issue, crashes, or maintenance, the entire cluster became unavailable until it was restarted. This created a single point of failure, which was a serious risk for production environments. To address this, Hadoop introduced high availability. In this setup, the cluster runs two or more redundant name nodes in an active standby configuration. At any given time, exactly one name node is in the active state serving client request. The other name node remains in a standby state, fully synchronized and ready to take over immediately if the active fails. To keep the active and standby name nodes synchronized, both access a shared storage location, such as a shared NFS directory or a quorum of joiner nodes. Whenever the active name node updates the namespace, such as creating or deleting files, it writes those edits to the shared storage. The standby continuously reads these edits and applies them to its own state, ensuring it stays up to date. In modern high availability development, automatic failover is configured using Zookeeper and the ZK failover controller. Zookeeper monitors the health of each name node, detects failure, and helps elect which name node should become active. If the active fails, the standby takes over automatically with minimal disruption. By maintaining synchronized active and standby name nodes and supporting automatic failover, Hadoop high availability feature ensure that the cluster remains operational if a name node fails. This improves fault tolerance, reduces downtime, and enables seamless operation in large distributed environments. Now let's discuss the advantages and disadvantages of Hadoop. Let's start with the advantages. One of the biggest advantages of Hadoop is the scalability. Hadoop allows organizations to easily scale their storage and processing by adding more nodes to the cluster without major change to the existing system. Another key advantage is cost efficiency. Hadoop is Hadoop is open source and runs on commodity hardware, which significantly reduces infrastructure cost compared to traditional data system. Hadoop also provides fault tolerance. Data in Hadoop is replicated across multiple nodes, so even if a node fails, the data remains available and processing continues without interruption. Hadoop supports parallel processing, allowing large datasets to be processed faster by distributing work across multiple nodes in the cluster. Now let's look at the disadvantages. One major disadvantage of Hadoop is high latency. Hadoop is designed for batch processing, so it is not suitable for applications that require real-time or low latency data access. Hadoop also has a complex ecosystem. Setting up configuration and managing a Hadoop cluster requires specialized skills and can be challenging for beginners. Another limitation is that Hadoop is not ideal for small datasets. The overhead of distributed processing can make Hadoop inefficient when working with limited data volumes. Security configuration in Hadoop can also be complex, especially in large production environments, where authentic and authorization must be carefully managed. So that's it. That's all about Hadoop and its components. Don't forget to like, comment or subscribe. Thank you for watching and see you in next video.